Hi class, finally we got the chance to go through the Doppler effect. I thought it's better for me to record the video in case due to some unforeseen circumstances I have to leave class and then we wouldn't have time tomorrow to go through the Doppler effect. So let's go through Doppler effect again. Remember the equation is actually F apparent or F, just call it FA, equals to F naught V of sound plus minus V of observer over V of sound minus plus V of source. So let's say, for example, if we have a case where you have light from a source. The source is not moving and the observer starts to move towards the light source. Now we're talking about light, not sound, at a speed V. So since the source is not moving, you have speed of light, not source, not sound now, plus. Why plus? Because the observer is moving towards the source. That's why we choose plus. If it is moving away, we have chosen minus. V over here divided by the speed of light. The V of source is 0. So if you take a look at this equation, it will be F naught 1 plus V upon C. And if we rearrange the equation, it will be Fa minus F naught, which is delta F, is equals to F naught V upon C. And hence, delta F upon F is equals to V upon C, and that's the equation in your notes. Then some students may ask, what if I have a moving source instead of a moving observer? So then you will have this case where the light source is here and it moves with a speed V and the observer is stationary. So then what we have is F apparent equals to F naught V, or rather C over C minus V, which is equals to F naught 1 over 1 minus V over C. Now, there is a very important approximation in this derivation, that is, we assume that V is very much smaller than C. Now, if V is very much smaller than C, then this term over here is going to be very small. And there is a very powerful approximation that we can make, which is 1 minus nx if x is small. And we're going to use that in this scenario. So Fa is going to be equals to F naught 1 plus V upon C. Why plus? Because this is to the power of minus 1. So minus 1, if you bring down, which is the n over here, if this is minus 1 minus, then you're going to have plus. So it's going to go back to the same scenario that we have earlier on, equals to V upon C. So what I'm trying to show you is that it is true whether it is for source moving or observer moving. Now, next level that we're talking about over here is that some of you may cringe at the fact that we're assuming V upon C to be small. What if V upon C, hang on. Basically what we are doing over here is to apply what is applicable for sound to light. But we all know that if an object were to move at speed that's high enough, then relativistic effect will come into play. So if you're talking about speed that's high enough, the actual equation is this. Fa is actually equals to F naught square root 1 plus beta over 1 minus beta, where beta is equals to V upon C. Now this is the relativistic Doppler effect. So it is quite different from the form that we saw. At least with the square root sign, it is quite obvious it is different. So how will this, or whether will this reduce to the form that we talk about over here and over here, is what we're going to try to prove. That as speed small enough, as speed much lesser than your speed of light, it goes back to what we derive over here, which is using the sound model. Alright, so let's take a look. Equals to F naught, if V upon C is very small, then we have 1 power beta, 1 minus beta to the power of half to the power of half, which is equals to F naught. Using the approximation method, it is 1 plus beta, 1 plus half beta, which is equals to F naught 1 plus beta plus 1 quarter beta square. Now, if beta is small, then we can actually approximate beta square to be 0. So it's F naught 1 plus V upon C, Fa. As you can see, it will be Fa minus F naught equals to F naught V upon C, which is delta F upon F equals to V upon C. So it's the same equation that we derived just now. That is the, I'm trying to prove that the approximation method that we use using the sound method is actually a very good gauge if the speed is very much smaller than the speed of light. Alright, so let's anchor these equations with an example. So let's say, for example, a person would travel towards a traffic light and claims that as he travels towards the light, the wavelength shortens and the frequency goes higher. So if you were to claim that it goes from red, green, if you go towards the red light fast enough, you actually see a green light. So what's the speed that the person is traveling at if this claim is true? Now, let's assume that the wavelength of red light is 700 nanometers. The wavelength of green light, say for example, is about RGB in the middle, so it's about 550 nanometers. Then what would be the speed required? So delta F upon F is equals to V upon C. So V will be equals to C times the difference in frequency, which is speed of light divided by wavelength, 550 nanometers, minus speed of light, 700 nanometers, divided by the original frequency, which is that of red, 700 nanometers. So the C will cancel off, which is equals to the speed of light multiplied by 700 minus 550 divided by 700 times 700. Divided by 700 times 550 multiplied by 700. So the 700 cancels off, which is C times 150 divided by 550. We're talking about 311, so it's about 30%, 20+% of the speed of light. It's impossible, basically. So, well, not to try to prove that you can use this as a mitigating factor in the law, in the court of law, but I'm just trying to show you that actually if you perform this kind of calculation for this kind of context, the speed of that you need to travel at is about 20+% the speed of light, which is really, really fast. It's about 10 to the power 7 meters per second. Your rubbers will fly. So I hope that through this lesson, very short lesson, you would have gathered understanding of how to apply Doppler's effect equation, which is predominantly used for sound in the context of light or EM waves. And I've also shown you that the correct equation, the proper equation, which is taking into account the relativistic effect when you travel near the speed of light, that if you assume that the speed is small enough, it actually reduces to the same equation. And I've gone through one example to show you how this can be applied in situations. So I hope that this will give you a good grip on the use of Doppler effect for EM waves. Alright, thank you.